What actually happens at a black hole singularity? The very phrase seems to whisper of endings, of collapse, of a place where nature abandons reason and mathematics dissolves into silence. Yet the truth is far more profound and far more unsettling than popular imagination suggests. A singularity is not simply a cosmic drain swallowing light and matter into oblivion. It is a boundary of understanding, a frontier where the elegant architecture of space-time, described so precisely by Einstein's equations, folds inward upon itself. To confront the idea of a singularity is not merely to explore astrophysics, it is to face the limits of knowledge itself, and to recognize that the universe is more subtle, more structured, and more mysterious than our instincts would ever predict. In classical general relativity, gravity is not a force in the traditional sense, but a curvature of space-time caused by mass and energy. When a massive star exhausts its nuclear fuel, nothing remains to counteract the relentless inward pull of gravity. The star collapses. If its mass is sufficient, no known pressure can halt this implosion. According to the mathematics, the curvature grows without bound. Density increases toward infinity. Space-time narrows into a point of infinite compression. This predicted state is what we call a singularity. It is not described as a location within space, but rather as a place where space itself ceases to be well defined. The equations indicate a breakdown, a signal that something extraordinary occurs beyond the veil of the event horizon. Yet singularities are not speculative fantasies conjured from loose calculations. They arise from rigorous theorems developed in the 20th century, demonstrating that under very general conditions, gravitational collapse inevitably leads to such extreme outcomes. These theorems reshaped our understanding of cosmic destiny. They revealed that singularities are not rare mathematical curiosities. They are natural consequences of gravity's logic. If general relativity is correct, then singularities are woven into the fabric of the cosmos. And this realization carries philosophical weight. It tells us that the universe contains boundaries that classical reasoning alone cannot cross. The triumph of physics, paradoxically, leads us to its own horizon. But what does it mean for curvature to become infinite? Infinity in physics is rarely a literal statement. It is often a warning sign, an indication that a theory has been pushed beyond its domain of validity. When temperature calculations once predicted infinite energy in blackbody radiation, the solution was not that nature truly harbored infinite heat. Instead, a deeper framework, quantum mechanics, emerged to restore coherence. In the case of singularities, the infinities suggest that classical general relativity, magnificent though it is, cannot be the final word. The singularity may not represent a physical object at all, but rather a limit of description, a place where our current mathematical language fails. Inside the event horizon of a black hole, the structure of space-time is radically altered. The roles of space and time shift in ways that challenge intuition. The path toward the singularity is not merely a direction in space, it becomes as unavoidable as the flow of time itself. Just as we cannot prevent tomorrow from arriving, anything within the horizon cannot avoid progressing toward the singularity. This inevitability gives the singularity a haunting character. It is not simply hidden, it is inescapable for anything that crosses the threshold. The geometry dictates destiny. And yet, we must remember that this conclusion arises from equations that do not incorporate quantum principles, leaving open the question of what truly occurs in that extreme regime. As matter collapses inward, tidal forces grow immense. Differences in gravitational pull between neighboring points stretch and compress objects with extraordinary intensity. Near the singularity, these tidal effects would become catastrophic, dismantling atoms and subatomic structures. But as we approach scales smaller than atomic nuclei, quantum effects cannot be ignored. At these distances, uncertainty principles and quantum fluctuations begin to dominate. Space-time itself may no longer be smooth and continuous. Instead, it could exhibit a granular or probabilistic character, fluctuating in ways that classical geometry cannot capture. The singularity thus becomes less a pinpoint of infinite density and more a signpost pointing toward a deeper, unified theory. And here lies the profound suspense at the heart of modern physics. If singularities signal the breakdown of general relativity, then what replaces it? What hidden structure lies beneath the classical continuum? Quantum gravity, still incomplete, aims to reconcile the curvature of spacetime with the discrete nature of quantum mechanics. Perhaps the singularity is resolved into a finite, though unimaginably dense configuration. Perhaps collapse halts before infinity is reached. Or perhaps spacetime transitions into a new phase altogether, beyond our current imagination. The singularity stands as a silent challenge, daring us to extend our understanding further. It is not merely a cosmic endpoint, but an invitation to rethink the foundations of reality itself. If we pause at this threshold, we begin to sense that the singularity is not only a destination in space, but a mirror held up to human thought. It asks whether our mathematical descriptions are discoveries of ultimate truth or approximations that dissolve under sufficient pressure. The singularity theorems revealed something astonishing, that gravitational collapse does not depend on perfect symmetry or idealized conditions. Even irregular, distorted stars, subject to turbulence and asymmetry, are driven by gravity toward a boundary where classical predictability ends. This universality gives singularities a strange inevitability. They are not rare accidents. They are encoded into the logic of space-time itself, as long as we trust the equations without modification. And yet, there is an irony embedded in this inevitability. The same mathematics that predicts the singularity also predicts its own collapse at that point. Curvature scalars diverge, geodesics terminate. Time, as measured by the paths of particles, reaches an abrupt conclusion. We encounter not a physical object we can observe or measure, but a region where the language of classical geometry loses coherence. It is as though space-time, the very stage on which physics unfolds, folds inward and erases its own script. This is not merely a dramatic statement, it is a precise mathematical outcome. The equations signal that something fundamental must change. In the middle of this realization lies a deeper suspense. Suppose we insist that the singularity is real, that infinity truly manifests in nature. What would that mean? An infinite density would imply an infinite gravitational field, an infinite curvature of spacetime. Such infinities threaten to unravel causality itself. If physical quantities become unbounded, predictive power vanishes. Science depends on finite relationships, on quantities that can be compared and calculated. An actual infinity at the heart of a black hole would represent not just a physical extremity, but a philosophical rupture. It would suggest that the universe contains regions where explanation is permanently impossible. But physics has a history of transforming infinities into insights. When classical electromagnetism predicted infinite self-energy for point charges, quantum theory provided new structure. When thermodynamics approached absolute zero, quantum statistics clarified behavior. In each case, infinity was not an endpoint, but a signpost. The singularity may function in the same way. It signals that gravity, when compressed beyond a certain threshold, must be governed by principles not yet fully understood. Quantum gravity is not a luxury or a speculative indulgence. It is demanded by consistency. The singularity forces our hand. It tells us that the unification of quantum mechanics and space-time curvature is not optional. Imagine the collapsing core of a massive star as it shrinks past atomic scales. At those depths, quantum fluctuations of space-time itself may become significant. Instead of a smooth manifold, space-time could behave like a dynamic, fluctuating network. The concept of a precise location may dissolve. Distances and durations might lose their classical meaning. The singularity in this view would not be a point of infinite density, but a transition into a regime where geometry is fundamentally quantum. The collapse does not necessarily end in a mathematical singularity. It may approach a quantum gravitational state that replaces infinity with a new form of order. Here the suspense intensifies. What if the interior of a black hole is not a dead end, but a doorway? Some theoretical proposals suggest that quantum effects could prevent total collapse, creating a bounce or a bridge to another region of spacetime. Others propose that information, rather than being destroyed, is subtly encoded on the event horizon. These ideas remain speculative, yet they arise from a serious attempt to preserve the coherence of physics. The singularity becomes a testing ground for the deepest principles we hold. Does information survive? Does causality remain intact? Or must we revise our most cherished assumptions? The mystery grows even more profound when we consider the origin of the universe itself. Cosmological models indicate that, when traced backward in time, the entire observable cosmos emerges from an initial singularity. The same mathematical structure that predicts black hole singularities also predicts a beginning of infinite density and curvature. This parallel is not accidental. It reveals a symmetry between collapse and creation. The singularity is not merely an end, it may also be a beginning. If classical spacetime breaks down at both extremes, then understanding singularities is inseparable from understanding our cosmic origin. And so we stand at a crossroads. On one path lies the acceptance that singularities represent the final limits of explanation, permanent horizons beyond which reason cannot pass. On the other path lies the conviction that deeper structure awaits discovery, that infinity is not the last word, but a clue. The history of science encourages the second view. Every apparent boundary has eventually revealed new layers of order. The singularity challenges us not to retreat into mystery, but to advance into deeper coherence. It compels us to refine our mathematics, to rethink our assumptions, and to embrace the possibility that reality is subtler than even our most elegant equations suggest. To continue this journey is to recognize that the singularity is not merely a technical issue buried within theoretical equations, but a profound statement about the unfinished nature of human understanding. We often imagine science as a steady accumulation of certainty, a tower rising higher with each discovery. Yet the singularity reminds us that progress sometimes reveals abysses rather than summits. The deeper we penetrate into gravitational collapse, the more clearly we see that our intellectual frameworks are provisional. This is not a weakness of science, it is its greatest strength. A theory that reveals its own limits invites transformation. The singularity stands as a quiet declaration that reality exceeds every model we construct. Consider what it means for spacetime itself to become unstable under extreme conditions. In everyday experience, space feels continuous and time flows uniformly. General relativity elevated this intuition into a magnificent geometric structure where mass shapes curvature and curvature guides motion. But near a singularity, curvature grows so intense that the smooth fabric tears in a conceptual sense. If quantum gravity intervenes, it may reveal that space-time is not fundamental at all. It could be emergent, arising from deeper principles, in the way temperature emerges from microscopic motion. The singularity would then mark the scale at which the illusion of continuity dissolves into discrete structure. This possibility carries extraordinary philosophical consequences. If space-time is emergent, then the singularity is not a point where something physical becomes infinite, but a boundary where one description yields to another. The collapse of a star would not culminate in a literal point of zero volume. Instead, it would approach a regime governed by quantum geometry, where new variables replace classical coordinates. The infinities vanish because the language that produced them no longer applies. Just as the concept of a perfectly rigid body fails at atomic scales, the concept of smooth spacetime may fail at Planckian depths. The singularity becomes a threshold of transition rather than annihilation. Yet we must not underestimate the magnitude of this challenge. A consistent theory of quantum gravity has eluded physicists for decades. Approaches differ in mathematical structure and philosophical interpretation. Some suggest spacetime is woven from fundamental loops or networks. Others propose vibrating entities whose interactions generate geometry. Each framework attempts to tame the infinities predicted by classical relativity. Each seeks to preserve coherence where the singularity threatens breakdown. The suspense persists because no proposal has yet achieved definitive empirical confirmation. We are explorers mapping the shoreline of an unseen continent. In this uncertainty lies a powerful lesson about intellectual courage. The singularity confronts us with ignorance, but not with defeat. It encourages humility without surrender. When equations predict infinity, we do not conclude that understanding is impossible. Instead, we infer that our description is incomplete. This mindset has driven every revolution in physics. It is the willingness to question even our most successful theories that propels discovery. The singularity, therefore, is not an embarrassment to science. It is a catalyst. It sharpens inquiry and directs attention toward unification. There is also a deeper existential resonance in contemplating singularities. They remind us that boundaries are not merely obstacles, they are invitations. The event horizon of a black hole conceals its interior from external observers, yet it does not extinguish curiosity. Likewise, the mathematical horizon represented by a singularity conceals deeper structure, yet it ignites imagination. Human progress has always advanced by confronting limits. We cross oceans, decode genomes, and unravel cosmic radiation because we refuse to accept that horizons are final. The singularity stands as the ultimate horizon, urging us to extend reason into realms once thought unreachable. As we reflect on what actually happens at a black hole singularity, we arrive at a subtle conclusion. Classical physics predicts infinite curvature and density, signaling its own breakdown. Quantum gravity likely intervenes, replacing infinity with new structure. The precise mechanism remains unknown, suspended between competing theories and awaiting experimental insight. But the direction is clear. The singularity is not a physical object we can describe in isolation. It is a message encoded in mathematics, declaring that the union of gravity and quantum principles is essential for a complete picture of reality. It is less a destination than a demand for deeper unity. Ultimately, the study of singularities transforms our understanding of both cosmos and self. It teaches that certainty is provisional, that infinity is often a signpost, and that the pursuit of knowledge is an ever unfinished journey. Black holes, once feared as cosmic abysses, become laboratories of extreme thought. Their singularities challenge us to reconcile continuity with discreteness, geometry with probability, determinism with uncertainty. In facing these challenges, we refine not only our theories but our perspective. We learn that mystery is not the opposite of understanding, it is the birthplace of it.